This video is for those of you who are studying for the first exam of organic chemistry. And it covers topics typically taught in the first 4 chapters of a typical organic chemistry textbook, such as functional groups, Drawn-Lewis structures, hybridization, sigma and pi bonds, resonance structures, acids and bases, Newman projections, boiling point, and chair conformations. So let's go ahead and begin. Number 1, glutathione, abbreviated for GSH, is a tripeptide molecule composed of 3 amino acids, glutamic acid, cysteine, and glycine. It functions as an antioxidant capable of neutralizing free radicals and plays a role in detoxification. Which of the following functional groups is not found in glutathione? So here, this right here is known as a carboxylic acid. It's abbreviated COOH. This group here is also a carboxylic acid. It can also be represented as CO2H. So we could eliminate answer choice A. This here is an amine, so we can cross out answer choice C. And this part here is an amide. Whenever 2 amino acids join together to form a dipeptide, di means 2, tri means 3, it forms an amide linkage. So if you have a peptide with 1 amide linkage, that means that there were 2 amino acids that join together to form that dipeptide. Glutathione has 2 amide functional groups. So that means that 3 amino acids join together to form this tripeptide. So whenever you see a carbonyl group adjacent to a nitrogen, that's an amide functional group. So we could eliminate answer choice E. This group here, whenever you see RSH, that is a thiol. It is the thiol part of glutathione that gives its ability to work as an antioxidant. This is glutathione in its reduced form when it has a thiol functional group. When 2 thiols get together and they're oxidized, they form a disulfide bridge. So this is the oxidized state of glutathione, and this is the reduced state of glutathione. So that's a thiol, which means we can eliminate answer choice D. What we don't have is a ketone. A ketone looks like this. It's just a carbonyl group. Now the R group has to be a carbon. So this is not a ketone because the R group here is not a carbon. So that makes the carboxylic acid. This is not a ketone because the adjacent nitrogen makes it an amide. But if these 2 were simply carbon atoms, then this would be a ketone. So the correct answer for number 1 is answer choice B. Number 3, draw a Lewis structure for each molecule shown below. So let's start with the first one, CH3CN. So first we have CH3. Carbon likes to form 4 bonds, and hydrogen can only form 1 bond. So this is going to be our CH3, and then it's attached to a carbon, which is attached to a nitrogen. Now keep in mind, carbon likes to form 4 bonds, nitrogen likes to form 3. The only way we can make this work is if we put a triple bond between the carbon and the nitrogen. So that carbon has 4 bonds and nitrogen has 3. Now, nitrogen needs 8 electrons to satisfy its octet requirement, so it needs a lone pair. Each bond represents 2 electrons. We got 2, 4, 6, 8 electrons. So here's some things you need to know when drawing Lewis structures for organic compounds. Hydrogen always forms 1 bond. If carbon is neutral, typically it will form 4 bonds. When carbon has a negative charge, or when it has a positive charge, it usually will form 3 bonds. When oxygen is neutral in charge, it will typically form 2 bonds and 1 lone pair. Nitrogen, when it's neutral, will usually form 3 bonds and a lone pair. So when there's a negative charge, typically it's going to have 1 less bond and an additional lone pair. So for instance, when oxygen has a negative charge, it's not going to have 2 bonds, it's going to have 1 bond and an extra lone pair, so it's going to have 3 lone pairs. When nitrogen has a negative charge, instead of 3 bonds, it's going to have 2 bonds and 2 lone pairs. When oxygen has a positive charge, it's going to have 1 less lone pair and 1 additional bond relative to its neutral state. So this is oxygen when it has a positive charge. It has 3 bonds and 1 lone pair. Nitrogen, when it has a positive charge, is going to lose the lone pair, gain a bond. So it's just going to have 4 bonds. So those are the things you want to know when drawing common Lewis structures of organic compounds. Now let's move on to number 2, C2H2. Now, because there's 2 hydrogens, it's unlikely that both of those hydrogens will be on the same carbon. So it makes sense to put 1 hydrogen on each carbon. Now, in order for carbons to have 4 bonds, we have to put a triple bond in the middle. So C2H2 is this structure here, acetylene. Now what about for compound number 3? How can we draw the Lewis structure for C6H5CH2N2? Whenever you see C6H5, you're dealing with a phenyl ring or a benzene ring. So benzene has 6 carbon atoms and it has 6 hydrogen atoms. However, because we only have 5, that means this benzene ring has replaced a hydrogen with a substituent, which is what we see here. The other 5 hydrogens, we don't have to show them, but just so you can see it, I'm going to put it on the screen. Next, we have a CH2 and then N2. Whenever you see N2 attached to a carbon, think of nitrogen gas. Nitrogen gas is a diatomic molecule that looks like this. The only difference is this lone pair is going to be replaced with a bond. So that's the Lewis structure for C6H5CH2N2. Now we do need to incorporate formal charge. When nitrogen has 3 bonds, it's going to be neutral. But when it has 4 bonds, it's going to have a positive formal charge. So this is the final answer. So there should be a plus charge here. Now let's move on to number 4, CH3COCH3. So drawing it from left to right, we have a CH3, a methyl group, which looks like this. Then we have a carbon attached to an oxygen. We can't draw it like this because this carbon won't have 4 bonds. The only way to make this work is to make a double bond with this oxygen. Keep in mind, oxygen likes to form 2 bonds, and then attach the CH3 here. So drawing it this way, every carbon atom has 4 bonds, and oxygen has 2 bonds, and then we need to add the 2 lone pairs on the oxygen. So what we have is a ketone functional group. It looks like I wrote the same problem twice, but this should be something different. CH3 CO3H. Go ahead and try that one. So starting with the methyl group, CH3, and then we have a carbon with 3 oxygen atoms. How can we do this? Well, it wouldn't make sense to put the 3 oxygen atoms like this, because if we put the hydrogen here, carbon has 4 bonds, but these 2 oxygen atoms, they only have 1. So that's not going to work. If we can't do this either, because that will be 6 bonds. The only way to make this work is to have 1 carbonyl oxygen and the 2 other oxygen atoms like this. In this structure, every carbon atom has 4 bonds, every oxygen atom has 2 bonds and 2 lone pairs, and hydrogen has 1 bond. This is what is known as a peroxy acid. So think of a carboxylic acid, which looks like this, and think of an organic peroxide, which looks like this. So the peroxy acid, it has elements of a carboxylic acid and a peroxide, so it's called peroxy acid. For number 6, we have a CH3 attached to a CO2, so we have a carbon. Now how should we arrange the 2 oxygen atoms? We can't do it this way because carbon will only have 2 bonds, and we have to put the CH3 here. If we were to put the CH3 here, carbon will still have just 3 bonds and not 4. The only way to make this work is to do it like this. In this way, every carbon atom has 4 bonds, and each oxygen atom has 2 bonds and 2 lone pairs. So what we have here is the ester functional group. Now, moving on to number 7, we have a CH3 that's attached to 3 methylene groups, 3 CH2s, and then a CHO. Whenever you see CHO, that's an aldehyde. It's a carbon with a double bonded oxygen and a hydrogen. So that's our aldehyde functional group. For the last one, number 8, we have 2 methyl groups. We can't do this and then attach it to the CH. This carbon will have 5 bonds, which doesn't happen. What we want to do is we want to start with the CH carbon. So we have a carbon that's attached to 2 methyl groups. So you can show it like this. And then that carbon has a hydrogen, and then it has this group. But I'm going to redraw it. So let's start with the CH carbon. Let's put the hydrogen here, and let's put the first methyl group here and the second methyl group here. Next, we can move on to this carbon atom, which has an oxygen and an NH2 group. We can't connect it like this because carbon won't have 4 bonds. So we need a carbonyl carbon and then the NH2 group. When nitrogen has 3 bonds, it's going to have 1 lone pair. When oxygen has 2 bonds, it will have 2 lone pairs. So this represents our amide functional group. So that's it for number 3. Now you know how to draw Lewis structures for common functional groups. Now for those of you who are interested in getting the full video with all 90 practice problems, feel free to check the description section below this video. Number 14. Identify the hybridization of the indicated atoms shown below from left to right. So what is the hybridization of hydrogen? Now hydrogen is unique. That technique that I showed you doesn't really work, so I'm going to show you another one. Let's say if you have methane. Methane has 4 groups around it. 1, 2, 3, 4. The hybridization is going to be S1P3. If you add 1 and 3, you get 4. Now this is formaldehyde. The hybridization of the carbon for formaldehyde is going to be 1, 2, 3. It has 3 groups. So it's going to be S1P2. 1 plus 2 gives you 3. Let's say if you have PCl5. We're kind of jumping into general chemistry. Here the phosphorus atom has 5 groups around it. It turns out that the hybridization at the phosphorus atom is going to be D1S1P3. 1 plus 1 plus 3 adds up to 5. So notice that the sum of the exponents will usually add to the number of groups of the atom of interest. Here's another example. Sulfur hexafluoride. The sulfur atom has 6 groups, and it turns out that the hybridization is D2S1P3. 2 plus 1 plus 3 adds up to 6. Now, lone pairs are counted as well. In the case of water, which has 2 lone pairs, the oxygen has 4 groups. 1, 2, 3, 4. 2 atoms, 2 lone pairs. And it turns out that the hybridization on the oxygen is S1P3. 1 plus 3 is 4. Another example is ammonia. Ammonia has 3 atoms. Well, the nitrogen is attached to 3 atoms. Ammonia has a total of 4 atoms, rather. But the nitrogen has 3 atoms, 1 lone pair. So if we count it, that's 4 groups. The hybridization at the nitrogen atom is S1P3. Now, let's go back to methane. What about the hybridization of hydrogen? If we look at hydrogen, hydrogen is only bonded to 1 atom, so it has 1 group. So it's simply just S. Hydrogen doesn't have a p orbital. It's a first row element. It only has an S shell. So the hybridization for hydrogen will always be S. So this is going to be S. Now for the carbon atom, it has 1 pi bond, so we know it's going to be sp2 hybridized. Or you can see it this way. This carbon has 3 groups. 1, 2, 3. So it's S1P2 hybridized. 1 plus 2 is 3. The oxygen atom, it has a pi bond too. So it's going to be sp2 hybridized. Or you can see it this way. It has 1 group and 2 lone pairs, so a total of 3 groups. So it's S1P2 hybridized. 1 plus 2 is 3. Now the triple bonded carbon atom, that has 2 bonds. I said binds. It has 2 bonds, so it's going to be sp hybridized. The CH2 carbon has no pi bonds, so it's going to be sp3 hybridized. If you draw it out, the carbon is attached to the triple bonded carbon, the OH group, and it has 2 hydrogen atoms, so it has 4 groups. 1, 2, 3, 4. So it's S1P3 hybridized. 1 plus 3 is 4. Finally, the oxygen atom with the lone pairs. This is the first group, second group, and then the 2 lone pairs. It has 4 groups, no pi bonds, so it's going to be sp3 hybridized. Number 18. The CC bond energy in ethane is 377 kilojoules per mole, and the CC bond energy in ethylene is 720 kilojoules per mole. Given this information, would you expect the pi bond in ethylene to be weaker or stronger than the sigma bond in ethane? So here we have ethane, and here we have ethylene. So this is the structure of ethane. We only have a single bond. And this is the structure for ethylene. Now we know the bond strength for ethane, that is the carbon-carbon bond strength, is 377 kilojoules per mole, and for ethylene it's 720 kilojoules per mole. Now the type of bond that we have, the CC bond, that's a sigma bond. Now the 720, it corresponds to two bonds. The double bond contains one sigma and one pi. So if we were to subtract the bonds in ethylene by the CC bonds in ethane, in ethylene it's one sigma and one pi, minus for ethane just one sigma bond. If we subtract these two, the sigmas should cancel and we can get an approximate energy for the pi bond. So the sigma and the pi in ethylene is 720 kilojoules per mole. The bond energy in ethane for the sigma bond is 377. So if we take the difference of those two numbers, we get 343. This is an estimation of the sigma bond energy that's found in ethylene. So you can think of it this way. This is just an estimation, by the way. It's not an exact number. So the first bond is the sigma bond. Think of the second bond as the pi bond. So the sigma is 3. First, this should be a pi, not a sigma. The sigmas cancel, so I need to correct that. So let's assume that the sigma bonds have the same energy, approximately 377. This pi bond would have an estimate energy of 343 because these two numbers will add up to 720. But notice that the estimation for the bond energy of the pi bond is less than that of the sigma bond. And because of that, that's why we would expect the pi bond in ethylene to be weaker than the sigma bond in ethane. Because if we take the energy for the sigma and the pi bond in ethylene and subtract it by the energy for the sigma bond, we should get an estimation of the pi bond, and that's less than what we see for the sigma bond. And so that's why we would expect that the pi bond in ethylene to be weaker than the sigma bond in ethane. So if you ever get a test question, just remember, if you're comparing just one pi bond with one sigma bond, generally speaking, the pi bond is weaker than the sigma bond. But if you're comparing a double bond versus a single bond, the double bond is stronger than the single bond. So just to recap, a triple bond is stronger than a double bond, and the double bond is stronger than the single bond. A sigma bond on an individual basis is stronger than a pi bond. That's what you need to know for your test. 25. Consider the resonance structures shown below. Which structure is the major resonance contributor? And which one is the minor resonance contributor? The major resonance contributor is going to be the more stable of the two structures. So would it be the structure on the left, let's call that A, or the structure on the right, which we'll call B? Which one is more stable? The real question is it better to put the negative charge on the nitrogen atom or on a carbon atom? Which situation would create a more stable structure? Now, on the periodic table, we have carbon, nitrogen, oxygen, and fluorine. Electronegativity increases towards the right. Nitrogen is more electronegative than carbon. And we know that electronegativity is the ability of an atom to attract an electron to itself. Therefore, the atom that is more electronegative can better stabilize the negative charge than the atom that is less electronegative or more electropositive. So because nitrogen is more electronegative than carbon, it's better to put the negative charge on nitrogen than carbon, because nitrogen wants those electrons. It can handle the negative charge better. So this structure is more stable, which means that it's going to be the major resonance contributor. The structure that is less stable, that's going to be the minor resonance contributor. So the answer is structure B, the one on the right. Now, how can we draw the resonance hybrid? Because the true structure is not purely B, it's a mixture of A and B. Now, because B is more stable than A, the true structure is going to look more like B and less of A, but it's still somewhere in between. To draw the resonance hybrid, draw the parts of the molecule that don't change. So this alkene structure doesn't change, and in both structures we're going to have at least one bond. The NH group will stay the same as well. Notice that in both structures nitrogen has at least one lone pair, so that's going to stay. Now the pi bond can be here or it can be here. It's transitory. So the pi bond is actually shared between these three atoms. This carbon atom, that carbon atom, and the nitrogen atom. So that's what you got to do. You got to draw where the pi bond can be, but you use a hyphen use dashed lines instead of a full line. Now this extra lone pair, we're not going to draw it because it moves around. Now what about the negative charge? The negative charge is shared among the nitrogen atom and this carbon atom. So what we can do is put an overall negative charge outside of the molecule, or we can say this is partially negative and this is partially negative. That shows that the negative charge is shared among this nitrogen atom and this carbon atom. But because nitrogen is more electronegative, most of the negative charge will reside on the nitrogen atom. Even though this carbon will have some negative charge, the majority of that negative charge will be on that nitrogen atom. Number 40. Which of the following effects explain why compound B is more acidic than compound A? Is it the inductive effect, hybridization, electronegativity, electron delocalization, or atomic size? What would you say? So the only thing that's different is the oxygen and the sulfur atom. We could eliminate hybridization because the hybridization of everything is the same. In both cases, we have an sp2 hybridized carbon. The oxygen and the sulfur, they're both sp2 hybridized. They both have one pi bond. So there's no difference in hybridization. So it can't be due to that. Is it electronegativity? Well, here's carbon, nitrogen, oxygen, fluorine. Here's sulfur, chlorine, bromine, iodine. electronegativity increases to the right and it increases up. Oxygen is more electronegative than sulfur, yet this one is the weaker acid because it has the higher pKa value. So this is the weaker acid, this is the stronger acid. So it can't be due to electronegativity. So we can eliminate answer choice C. Now, is it electron delocalization? Well, both of these molecules have electron delocalization. This lone pair can delocalize into the carbonyl group, and this one can do that too. So they both have electron delocalization, but that doesn't make the difference between the two acidities. Even though it makes both compounds acidic, it doesn't favor one of these. It doesn't favor compound B over compound A because they both have electron delocalization. As for the inductive effect, both of these groups are electron withdrawing groups. Oxygen has more of an inductive effect than sulfur because oxygen is more electronegative than sulfur. Yet compound B with the sulfur is more acidic, so the inductive effect, even though they're present, it's not the driving force or the main factor behind why B is more acidic. The only answer is atomic size. Sulfur is significantly larger than oxygen. Because sulfur is bigger, it has more room to stabilize the negative charge. So even though the electron delocalization is present in both of these compounds, sulfur is bigger than oxygen. So here's oxygen with the negative charge. And let's say oxygen takes up this amount of space. The positive charge is now on the nitrogen. If we draw the resonance structure for the other one, it's going to look like this, very similar. The nitrogen will also have a positive charge, but the sulfur atom is much bigger than the oxygen atom, and so it has more room to stabilize the negative charge, which means because of the size of sulfur, it can stabilize the conjugate base better. So this is a weaker base, this is a stronger base because the negative charge is more concentrated in a smaller region. So because the size of sulfur can stabilize the base better, we have a stronger acid, but a weaker conjugate base. So the answer is atomic size. Sulfur is significantly bigger than oxygen. It can better stabilize the negative charge, giving us a weaker, more stable conjugate base, which explains why B is a stronger acid. 53. Rank the following compounds in order of increase in boiling point. So which one's going to have the lowest boiling point and which one will have the highest boiling point? We know that straight chain organic compounds typically have the highest boiling point. The branched ones, they typically have the lowest boiling point. So with that being said, it's safe to assume that number 5 is going to be the highest. Now, which one would you say is the lowest? Which molecule has the lowest boiling point? What would you pick? If you pick number 3, you're close, but not quite. The lowest one is actually number 1. The reason why that has the lowest boiling point is because there's no hydrogen bond in here. Compound 3, even though it has significant branching, it still has hydrogen bonds. You still have the NH group. So it turns out that the lowest is going to be number 1 because it doesn't have hydrogen bonds. What do you think the second lowest is going to be? So now we look at branching. Looking at compounds 2 and 3, 3 has more branching than 2. So 3 should be next, and then 2. And looking at 4 and 5, both of these are straight chain amino compounds, but this one has 5 carbons, this one has 6. So number 4 needs to be in the middle. So now here are the actual numbers. The boiling point for diethyl-methylamine is 65 degrees Celsius. So that's the lowest one. Now the next one, neopentylamine, the boiling point for that is 81 degrees Celsius. Next we have ethylpropylamine, compound 2, and that has a boiling point of 90 degrees Celsius. Next we have pentylamine, that's compound 4, and its boiling point is 104 degrees Celsius. And the last one, hexylamine, the boiling point is 131 degrees Celsius. So when ranking compounds in order of increase in boiling point, one of the first things to look for is to see if there's hydrogen bonding, and if there isn't. Molecules with hydrogen bonds usually have a higher boiling point than molecules that do not contain hydrogen bonds. The second thing is to look at, which one has more carbon atoms. This one has the greatest number of carbon atoms. We have 6 carbon atoms. This one has 5. This has 5, 5, and 5. So because we have more carbon atoms here, that's going to give us the highest boiling point. Now, among compounds 1 through 4, which all have 5 carbon atoms, that's when we start looking at branching. A straight chain hydrocarbon is going to have a higher boiling point than a hydrocarbon that's branched. So remember, things that increases the boiling point are the presence of hydrogen bonds, increase in molecular weight if you have more carbon atoms in the hydrocarbon chain. If you have a straight chain alkanes have a higher boiling point than branch alkanes. And that's about it. 71. Draw the least stable conformation of 2-methylbutane along the C2-C3 bond and determine the relative potential energy of that conformation. So let's begin by drawing 2-methylbutane. So here it is. And now let's convert that into a condensed structure. So we have a CH3. This is a CH carbon attached to a CH3. And then we have a CH2 next to a CH3. So this is carbon 2, carbon 3. Now let's turn this into a perspective formula. So carbon 2 has a methyl on top, it has another methyl to the side, and it has one hydrogen. Now carbon 2 is connected to carbon 3. Carbon 3 has 2 hydrogen atoms. We can put one here. Let's put the other one here. And it has a methyl group. So now let's convert that into a Newman projection. So carbon 2 is the front carbon, carbon 3 is the back carbon. So on the front carbon, we have a methyl group on the top and another methyl group to the left, and a hydrogen on the bottom right. Now on the third carbon, we can rotate these 3 groups, the hydrogen, the 2 hydrogen atoms, and the methyl. So the question is, where should we put the methyl group to get the least stable conformation? To get the least stable conformation, we want the eclipse conformation, not the staggered conformation. And we want this methyl group to be eclipse to one of these two methyl groups. So let's put it here. That means that the other groups will be eclipsed by hydrogen atoms. So this is the least stable conformation of 2-methylbutane. Now let's calculate the energy profile for this conformation. So we have 2 methyl groups eclipse, so that's 11. HCH3 eclipse is 6, and 2 hydrogen atoms eclipse is 4. 6 plus 4 is 10 plus 11. So the relative potential energy for that structure is going to be 21 kilojoules per mole. So that's it for this problem. So now you know how to draw a Newman projection given the name of an alkane and the bond of rotation, and you also know how to calculate the relative energy of a conformation. 86. Convert the chair conformation into a bond line structure. So first, let's start with the generic structure of cyclohexane. Now, let's say this is carbon 1, 2, 3, 4. Now we have an ethyl group going up on carbon 1, so let's put it on a wedge. And we're going to count it, since we went clockwise, we're going to count it in the clockwise direction. Carbon 2, we have bromine. And bromine is going up just like the ethyl group, so they're going to have the same configuration. They're going to be on the wedge. On carbon 3, we have chlorine going up, so that's going to be on the wedge as well. And carbon 4, the hydroxyl group is going down, so that's going to be on the dash. So that's how we can convert a chair conformation into a bond line structure.